Stripping down science. The Naked Scientists.
This is a special podcast to supplement the Naked Scientists' 5th of August programme edition, in which we celebrated the successful arrival on the surface of Mars of the Curiosity rover. You sent in lots of questions for that programme, and there wasn't time to include all of them in the main show podcast. So here we have collected together those extra questions that John Zarnecki and David Blake, the two guests on the programme, were kind enough to answer for you. So here they are. Mark Tabone says, greetings from sunny Queensland. He's just rubbing in the fact we're having the worst summer in my lifetime. He says, given the temperature extremes on the surface of Mars, what design features are used to keep the rover components from freezing? And I'm also going to bring in John Zarnecki after you have answered, David, because he's obviously got a lot of experience of sending probes to very inhospitable places. But you first, David.
Okay, very good question. First of all, the nuclear power source on the back of the rover produces a bit over 100 watts of electrical energy, but it also produces about 900 watts of thermal energy. And they actually have a fluid loop that takes the heat from the radioactive source and runs it across what they call the rover avionics mounting platform, where all the instruments are connected. And so that keeps us inside the rover in kind of a shirt sleeves environment. Now, the instruments outside the rover do have to contend with this very bitter cold temperatures during the nights.
And John, what about your experience on Titan, where it's minus 180, whatever it is, degrees C?
Yes, I mean, you think Mars is tough, but Titan is a lot colder, I think. Well, thermal design of spacecraft is very often one of the most challenging parts of the whole business. In the case of the Huygens probe, as I guess is true with Curiosity, you've got two extremes. You've got the extreme heat generated by the high-speed entry into a planetary atmosphere, and then once you've landed on the surface, you've got extreme cold. So it's really all about, I would say, good design, good thermal design, and generally conserving the little heat that you generate within the probe. And you have to go to what, to me, as a scientist, seem like ridiculous lengths. You even worry about the tiny amount of heat that is conducted down a very, very thin electrical cable. And you have to use special electrical cable, which is a good electrical conductor but a poor thermal conductor. So attention to detail at the minutest level.
Just while you're there, John, let's hear about Cassini-Huygens first, and then we'll ask about Curiosity. Aaron Page is saying he's wondering about the cost to pull off these missions. How much did your mission cost?
Well, it was a snip, to be honest. I think Cassini-Huygens, the whole thing, I'm talking round numbers here, was about 4.5 billion euros or dollars, about the same, of which a quarter or 20% was spent in Europe. Now, you've got to remember that was over probably 15 years. Spread out amongst, if you add up all the citizens of the US and Europe, that's, 700 million people. It works out at something like a couple of cups of coffee per person per year. And remember, that money is spent not on Mars or on Saturn, it's spent on Earth. And it's spent mostly in high-tech industry, paying people and paying industry to develop technology. So I think it's money well spent. And in the grand scheme of things, it's not a vast amount of money.
And same question to you, David. How much is the Mars Science Laboratory costing?
I guess end-to-end, about $2.4 billion, about equivalent euros. Same answer, kind of. This was spent over about 10 years, over 7,000 scientists and engineers, and we get the same kind of result. I think in the U.S. they make a comparison to people spend more money on bubblegum than they do on NASA, and people spend more money on beer advertising than they spend on NASA. So it's even though it sounds like a huge sum of money divided by the total amount over the population, it's really not very much compared to other things, and we really get great benefit out of it.
Yes, indeed. Paul Hunter has asked us via Facebook. You go to facebook.com/TheNakedScientist. Will the Mars Curiosity rover have the same longevity of Voyager 1, which 34 years after launch is still producing data?
Well, we sure hope so. I think I'll be well retired by then. But it is nuclear powered, so we won't have a problem of solar panels getting covered with dust. I guess really the only issue we're going to have is that same nuclear power that keeps us going is also going to be firing off neutrons at us at a rapid rate, and those neutrons can cause damage over time. So we're kind of in a race to get as much information as we can, and if we last 10 years, we'll still be sending information back.
Dominic, maybe this is one that you can help us out with. Phil Reynolds is wondering, apart from commenting on the dust on panels, which obviously is not a problem with Curiosity because it has a radioactive power source, as we've been hearing, he's actually asking, how do astronomers know how far away a planet is? Because people say, it's X number of million or billion kilometres to wherever. How did they actually make those measurements?
We know the laws of gravity that the planets are orbiting under, and we can see how long it takes those planets to orbit around the Sun. And there's actually a very simple numerical relationship, according to Newton's laws of gravity, as to how long a planet should take to circle the Sun as a function of how far away from the Sun it is. And so that's how we've made, historically, estimates of how far away the planets are. In fact, in the last 20 years or so, we've started firing radar at Venus and Mars, which are the nearest planets to us, and we can time how long it takes those radar pulses to come back, and that tells us to within a matter of hundreds of metres where those planets are.
It's amazing to think you can do it with that level of accuracy. Interestingly, maybe you can comment on Michael in Ipswich's question just very briefly. He says, why have planets got almost all of the angular momentum of our solar system?
I think that's actually one of the real puzzles of our solar system, why the mass is all in the Sun, but the angular momentum is all in the planets that orbit around it. John?
Yes, I mean, something must have happened to bring that about, because, as you said earlier, the Sun and the planets formed out of one rotating disk of material. So something has happened to give us this situation where the angular momentum is in the planets rather than the Sun. So, theorists come up with all sorts of great theories involving viscosity and friction and so on to explain it away. But it's a perceptive question.
And finally, Theo Gibson has said, and maybe this is one for you, John, with the whole concept of Huygens coming down through the atmosphere of Titan. Why do ships lose contact when they are travelling down through an atmosphere?
Well, if you have a high-speed entry, you create a sort of pocket of ionised gas around your probe. The gas is heated up so much it becomes ionised. It's stripped of its electrons, and that is not transparent to radio waves. So you have a sort of a radio blackout. I mean, the same thing happens with vehicles re-entering the Earth's atmosphere. It happens with the shuttle. It used to happen with the shuttle, I think, and the Apollo vehicles. So that's the main reason. It's the state of the gas around a high-speed probe.
That was David Blake and John Zarnecki answering your questions, which were sent in to the Naked Scientists' 5th of August Exploring Other Planets edition of our main programme. You can find that programme, if you didn't catch it and you're now intrigued by having heard the answers to the questions that came in, at nakedscientists.com/podcasts, or you can go straight to our iTunes channel if you go to itunes.com/nakedscientists.